So let's start week 4 of Physico Chemical Processes for Wastewater Treatment. This is taught by Professor V.C. Srivastav from IIT Roorkee, and I am the TA of this course. I am Vaibhav Kabadwal, a PhD scholar from IIT Madras. So this is the lecture outline. We will study aeration and coagulation and flocculation. So we will solve MCQs, fill in the blanks, and few numericals. Let's start with the aeration. We will solve one numerical. The question is, a dechlorinated secondary effluent is placed in a storage basin until needed for reuse. If the initial DO concentration is 1.5 milligram per liter, estimate the time required for the dissolved oxygen concentration to increase to 8.5 milligram per liter due to aeration. The surface area and volume of the basin are 400 and 100 meter cube respectively. Throughout the time of the effluent storage, the basin temperature was recorded as 20 degrees Celsius, and the saturation concentration of oxygen at this locality is worked out as 9.09 milligram per liter. This is at 20 degrees Celsius. Previously, a sample of effluent under similar condition was used for the surface aeration test at 15 degrees Celsius, and the following values were observed. See the table below, that will be in the next slide. It is expected that the rate of oxygen transfer in real time would be the same as that of aeration test. Note, the saturation DO at 15 degrees Celsius is 10.2 milligram per liter and theta is 1.024. So this is the table which is given in the question. So time with time, the DO is given at different time intervals. So I will write the equation. The question is saying the dechlorinated water is given to us. So its initial DO is 1.5 milligram per liter, and I will write that will be better. So there are two types of data given. One is at 20 degrees Celsius, and other at 15 degrees Celsius. So the test is performed at 15 degrees Celsius, and we have to calculate time required to aerate from 1.5 to 8.5 milligram per liter. So the question simply says we need that initial C0 value, initial concentration of DO is 1.5 milligram per liter, and we need to find after aeration the concentration will be 8.5 milligram per liter. So we need to find the time, how much time will it take. But the data is given, the above data which is here, at 15 degrees Celsius. And what else is given? Let's see. 1.5. Okay, we need to increase the DO value till this. Due to aeration, the surface area and volume are also given. Surface area and volume. We will write surface area I think it is 400 meters square, and volume is 100 meter cube. DO saturated is also given. at 20 degrees Celsius, and theta, and uh, this this is, and these three values are also given. So theta will be 1.024 and deosaturated is 9.09 milligram per liter, and deosaturated I think 10 point how much? 10.2. 10.2 milligram per liter. These are the two sets of data given to us. Simply, we need to calculate the time to increase the oxygen concentration in water, that is dissolved oxygen concentration from 1.5 to 8.5 milligram per liter. So what we will do, we will find out the time from this data, or what we can do, we can find KLA value from this data. We will change the KLA value. Okay, I will tell this thing in the next slide, that will be easy. So from 15 degree Celsius data, we will find out KLA value, and then we will convert it, that KLA value, for 20 degrees Celsius, and then using the equation, we will calculate the time required. Okay. So again, I will start this uh, concept from the starting. The concept is, from the fixed law of diffusion, we derive this equation: dC by dt is equals to KLA Cs minus C. So this which we are talking about, deosaturated, we will write it as Cs. We'll write it as Cs. Okay, in this formula. So dC by dt is equals to KLA Cs minus C. So here KLA, this whole term is called overall mass transfer constant. This A value is A by B. That it is given, but it is not required here. So we'll not use this, because it will be same for 15 degrees Celsius and at 20 degrees Celsius both. So when we integrate this, we will get how much? We'll get an equation that will be ln Cs minus C naught Cs minus C is equals to KLA T. So after integration, this is the equation. So we will use this equation for solving this question. So what the process is, as sir told in the video lectures also. So if the water is given to us, it will contain some water, and it will contain some DO also. So what we will do, we will first remove DO using some chemicals, and we will remove DO, that is first step. Then we will re-aerate the water, or we can say wastewater. And this when we re-aerate, You will check at what time interval, how is the DO increasing. So this data is given in the question at 15 degrees Celsius. At different time interval, we are given the data at 15 degrees Celsius. So from this 15 degrees Celsius, we will calculate KLA value, and then we will find KLA value at 20 degrees Celsius, and then we will calculate time. So this is our procedure. Let's start this. So what we will do, we will plot using this equation. Using this equation, we know the CS. We know CS at 15 degrees Celsius. So at t is equals to 0, DO should be 0, or DO is 0, because we have removed all the DO. So we will start the test from DO is equals to 0. C0 will be 0. So here I will write CS is 10.24, I guess. CS is 10.2. CS is 10.2. C0 will be 0, and C will be given in this question. C is given. This is C. This is C. C0 is 0. C is given, and KLA we have to calculate. Time is also given, this. So what we will do, we will plot this. We will write the table like this. This is the time. This is DO concentration. And here is CS minus C0 divided by CS minus C. Here next column will be ln of this. CS minus C0 divided by CS minus C. So the first value is 0.8 at 5 minutes. First value is 0.8. So how will we calculate 10.2 minus, let me check the formula, CS minus C0. So it will be 10.2. C0 is 0 because we remove all the DO present in water, and then we start the test. 10.2 minus 0. 10.2 minus 0.8. Tell what is the value. 10.2 minus 0 divided by 10.2 minus 0.8 is coming as 1.085. So if you take ln of this value, it will be 0.081. 0.816. So this is at t is equals to 0. Like at different time interval, you have to calculate different ln value, this. And then you have to plot it with respect to time. So you will get, so this value is increasing. So this value will decrease with time. So ln of ln of this you have to plot with time, so you will get the curve like this. So from this straight line you have to calculate the slope, and this slope will give you what? Think the slope will give you KLA value. How? If you see this equation, it will be y is equals to mx, like that. So m will be slope, so m is equals to KLA, right? So this is the data which you will get. So, oh, I think I did a little mistake. Initial value will be 0. Let me correct. Yeah. So I wrote this for 5 minutes. Let me recorrect. Draw. So here it will be initially that this value will be 0. This value will be 0. 1, then here it will be 0. Then second value at 5 minutes. At 5 minutes will be this value. Now it is correct. So likewise we will plot this. This we understood. These two values we have calculated for 0 and 5. Likewise we will calculate it for all the time interval, and then we will plot the graph. If you plot the graph, it will look like this. Like the graph will be plotted between ln cs minus, it will be c naught, ln cs minus c naught divided by uh, cs minus c naught divided by cs minus c, and then we will get the slope, means KLA value, as 0.0703. So this value is at 15 degrees Celsius. Let me correct this if I can. So till now we have calculated KLA value at 15 degrees Celsius, 0.0703. Suppose if you want to calculate KLA value at T degrees Celsius, the formula is KLA at 20 degrees Celsius, theta to the power T minus 20. But here we need KLA value at 20 degrees Celsius. So what we will do, we will just do some mathematical calculation. At T degrees Celsius, theta to the power 1t minus t. So here T is how much? 15 degrees Celsius. So 15 degrees Celsius is nothing but 0.0703. Theta is 1 point, how much it was? Theta was 1.024. 1.024 to the power 20 minus t was 15. So here if you calculate, it will come as 0.0791 KLA at 20 degrees Celsius. So here we calculated KLA value as 0.079. Its unit is in day inverse. Day or sorry, maybe time inverse. Time inverse is how much? Minute. Its unit will be minute inverse. So now we calculated the KLA value at 20 degrees Celsius, and we know the formula ln Cs minus C naught divided by Cs minus C is equals to KLKT. So we need to calculate how much time is required to aerate the dechlorinated water from 1.5 milligram per liter to 8.5 milligram per liter. So how much time required to aerate 1.5 milligram liter water, dechlorinated water to 8.5 milligram per liter at 20 degrees Celsius. Here, so at 20 degrees Celsius, we know CS value will be 9.09 milligram per liter. C naught is given that initial value is 1.5 milligram per liter and C is 8.5 milligram per liter, and KLA value was 0.0791 minute inverse, and the formula is ln Cs minus C naught divided by Cs minus C is equals to KLAT. So everything is given. So you calculate P as ln 9.09 minus 1.5 divided by 9.09 minus 8.5 divided by 0.0791. So time required to aerate water is 32.29 minutes. This is the answer. So one thing to note or keep in mind is when we perform the test for calculating the KLA value, we need to first remove the dissolved oxygen and then we need to perform the test. But while solving the question, like at 20 degrees Celsius we solved, so we can directly use the initial value which is given to us and the final value which is required. So this is the difference. Now we will move on to coagulation and flocculation. So now we will solve some MCQs. Read the question. Coagulation and flocculation are used for dissolved solids. No. With floating solids. No. Inorganic circulable solids. No. Colloidal solids. Yes. Coagulation and flocculation is used for colloidal solids. So what are the properties of colloidal solids? Think what are the colloidal solids and where we studied those colloidal solids. In turbidity we studied about these solids. These solids will lie in the range between dissolved solids and suspended solids. Correct? Let me check. So what are the properties of colloidal solids? So first we studied about those solids studied about these solids in turbidity. So these are always in motion in Brownian motion. They are very small in size. They will cause scattering of light. And one of the most important thing for this section is they do not settle easily due to effect of gravity, under the effect of gravity. This is the important point. These are the properties of colloidal solids. What is thermal coagulation? Thermal coagulation. Thermal means heat. What is coagulation? Coagulation is nothing but aggregation of particles. So when we heat the water or wastewater containing suspended solids form bigger flocks and settle. This is thermal coagulation. In thermal coagulation, we heat the suspended material and they will form bigger flocks and settle. And it will settle under the effect of gravity. Next question. Coagulation and flocculation units are used for. Read the question. remove infectious agents, not directly but indirectly. Remove toxic compounds that have adsorbed on the surface of particles. Yes. Remove precursors to the formation of disinfection byproducts. Yes. Let me explain. So, when organic matter is present, so in the form of colloids, or then it can be infectious also. So we can remove it through coagulation uh, flocculation. And if we remove some colloidal particles, can cause toxicity also. That we can also remove. And third one is precursor to the formation of disinfection byproduct. So when we don't remove the colloidal solids, so this colloidal solids, like in the form of organics or organic matter, plus let's say disinfection with chlorine, they can form disinfection byproduct. So this organic matter in the form of colloids can form disinfection byproducts. So it can be removed. Disinfection byproducts can be removed if colloidal organic matter is removed. So the answer is all of the above. So during coagulation, what type of mixing is done? Type of mixing. Rapid mixing, rapid mixing or slow mixing? Think the purpose of the uh, the purpose of coagulation is to neutralize the charge. So for that we provide rapid mixing. Rapid mixing is done properly to disperse the coagulant and promote collision among coagulants and the suspended particles to achieve good coagulation. This is the explanation. Rapid mixing is the answer. So mixing in coagulation and flocculation is a unit operation or a unit process. Uh, Read this question again. This question is asking about mixing. So mixing means what? Physical forces are involved. Physical forces means unit operations. Means unit operation. But the mechanism of coagulation, like sweep coagulation, adsorption and charge utilization, These are unit operate. These are unit processes. Charge of coagulant. Charge of coagulants is dash to those of colloidal solids. So the charge of coagulants is to those of colloidal solids. Suppose this is the colloidal solid. It has surface charge of negative. So the charge, if I'm adding the coagulant, what should be its charge? So its charge should be opposite, so that it can neutralize the surface charge. Opposite. Fill in the blank. Dash may affect the coagulation. What? Overmixing or overdosing? Basically, both may affect, but overdosing may affect the coagulation. So it is more dominant. Overdosing may affect coagulation. So how? That we need to understand. Suppose surface has the negative charge. We are adding coagulant. Some quantity we are adding. It has neutralized all the charges, which is, so what if we add more? If we add more, let's say at t is equals to 0, negative charge. At t is equals to x, 0 charge. I will write it as no charge. At t is equals to x plus delta x, I am adding coagulant, okay, and it will be positive charge. So if I will overdose the coagulant, it will cause charge reversal. That's why overdosing it should not be done. The dose higher than the optimum dose can cause charge reversal. That is what we studied. That it will cause charge reversal. Read this. Mixing is provided. In flocculation, slow mixing is provided. So, the slow mixing is provided in coagulation after the charge is neutralized and the sticky layer is formed around the colloidal particles. So, slow mixing is provided to increase just increase the chances of forming the bigger flock, so that they can form bigger flock. The, because now their charge is neutralized and they have a sticky layer around their surface, and if we provide slow mixing, then there is a chance to agglomerate and then settle in the sedimentation tank. And but if you provide fast mixing, then the flock may break due to fast mixing. So what is the second question? Dash collide causing them to bond to produce. So they will produce visible flux. Visible flux. And microfloc particle collide causing them to bond to produce visible flux. So for this will be microfloc particles. Microfloc particles collide causing them to bond to produce visible flux. What is colloidal stability? Think what is colloidal stability? So suspensions that do not agglomerate naturally are called stable. See, understand this term. What does stability mean? Suppose these are two charged particles. Let's say a river is coming and it has some colloids. And I am taking from this river water, I am taking the sample and I am magnifying it here. So it has two charged particles. They do not agglomerate naturally. So this suspension is called stable. Factors contributing to particle stability. So what are these factors? Understand. So excessive large surface to volume ratio resulting from their small size. So first point is they are very small in size. So they have very large surface. They have large surface to volume ratio. Because of their small size and surface phenomena predominates over mass phenomena. So their surface area is greater than compared to large surface predominates over mass phenomena. So their mass is less, but their surface area is also more. So both statements are these are conveying the same message. Coagulants are used for. So what we studied in the previous question, stability, particle stability or colloidal stability. So coagulants are used. So if the particle is stable, if the colloid is stable, we have to destabilize it. How? We will add coagulant. So coagulants are used for destabilizing the colloidal particles. A is correct. Which of the following are associated with alum coagulation? What is alum coagulation? Well, when alum is used as a coagulant, then it is called alum coagulation. Simple. These are the choice. These are the four statements, and from these four statements, how many statements are correct? We have to figure it out. So, which of the following are associated with alum coagulation? So, a decrease in alkalinity of treated water. So, what happens? I will tell little bit. So, alum reacts with alkalinity. It reduces pH. It reduces alkalinity. it forms hardness, and it forms gelatinous precipitate. The equation we will see in the next online session, and then we will solve some questions also. So what happens? Alum when reacts with alkalinity, it reduces alkalinity, it reduces pH, it forms permanent hardness, and it forms gelatinous precipitate. So this is gelatinous precipitate, which is formation of hydroxide flocks of aluminum. So this statement is correct. Decrease in the alkalinity of treated water, correct. A slight decrease in the pH of the treated water, this is also correct. And increase in the permanent hardness, correct. So all the statements are correct for alum as a coagulant. So B is the correct answer. Colloidal particles can also be removed by. Think how colloidal particles can be removed by. These can be removed by high force centrifugation, and these can be removed through filter also. So what will happen in centrifugation? Centrifugal forces will act. Like in washing machine, we remove the we dry our clothes. That is due to centrifugation principle. So we rotate this, we rotate the water sample. So the colloid will come in a corner, and from that we can remove. And through filters also we can remove. What is the objective of coagulation? So what is the objective of coagulation? Read. The objective of coagulation and subsequently flocculation is to turn the small particles into larger particles called flocks. So the colloidal particles are very small in nature, we know. So to agglomerate them and to form a bigger size particle so that it can settle due to gravity. This is the objective of the coagulation. The pH at which net charge of total particle surface equals 0 is called. The pH at which the net charge of the total particle surface, that is colloidal surface, is 0 is called. Suppose this is the colloidal surface, it has negative charge initially. After some time when you add the coagulant, positive, let's say, the charge will be 0. Will be 0. So what is this called? This is called point of zero charge. Point of zero charge. The ionic strength compresses the double layer. What dash the ionic strength compresses the double layer? So sir has taught something. This is the potential. So if you increase the ionic strength, it will compress the ionic layer. It will compress the double layer. So it will compress distance, this is potential. So increasing, if you increase the ionic strength, it compresses it it compresses the double layer. Optimum coagulant dose can be calculated using. The question is asking about the instrument. Which instrument? Optimum coagulant dose. So what is optimum coagulant dose, by the way? So there is a dose when coagulation or we can say colloidal particles removal is maximum. The dose of coagulant at which the removal of colloidal particles is maximum, that dose is called coagulant dose. So at coagulant dose we will have minimum turbidity. And this dose is calculated by an instrument called jar test. How can the optimum coagulant dose be calculated using jar test? How can the optimum coagulant dose be calculated using jar test? So what we will do in jar test, it is a setup which generally consists of 6 beakers. One, two, three, 4, 5, 6, and it has assembly to mix it. So what we will do, we will fill it. I'm writing the step-by-step process. So we will fill the beaker, fill all the beakers, except one. We will vary the LM dose. Let's say dose, we will add coagulant at different dose, in different doses, in different container, in different beaker, and then we will provide fast mixing, fast and slow mixing. Then we will allow them to settle, and then we will find turbidity. So the jar or the beaker which gives us minimum turbidity, that dose we call as optimum. But one more thing we can do in the site or in plant when in actual we have to perform. We can optimize pH also. So for this optimum dose, we will fix the dose and we will change pH. We will vary pH. So we will vary the pH and we will do the same procedure. We will do the same procedure and we will check and we will again check the turbidity. The turbidity of jar which is given that jar which is giving us less turbidity, we will take that pH as optimum pH. Jar giving less turbidity, that will give us optimum pH. And for that optimum pH, then we again calculate optimum coagulant dose. Optimum pH again vary the dose and then find optimum coagulant dose. Now factors affecting coagulation. So what are the factors which can affect coagulation? Can dose affect the coagulation? Yes, we study. If dose is more, then it can cause charge reversal. If alkalinity is present, because alkalinity is consumed by alum, so it can affect the coagulation. pH can also affect the coagulation. So all of above is the correct answer. Coagulants used for the treatment of potable water exhibit the following characteristics. Coagulants used for the treatment of potable water exhibit following characteristics. So they are non-toxic at working dosage. They should be non-toxic. They have a high charge density. High charge density. They are insoluble in the neutral pH range. Correct. All of the above. They should be non-toxic, we know. They have high charge density, means they should have more charge per unit weight or volume. They are insoluble at in the neutral pH range, because if they will be soluble, we can directly drink them. We can. So it requires to be insoluble at neutral pH range. So that's why they should be insoluble. So that we can see or sense before drinking water. How much alkalinity will be destroyed if 100 milligram per liter of bulk ferric sulfate 20% whereas 20% iron by weight is applied to wastewater in the water treatment plant. How much alkalinity will be destroyed if 100 milligram per liter of bulk ferric sulfate 20% Fe by weight is applied to the wastewater treatment plant. So the question is saying how much alkalinity will be required if iron is 100 milligram per iron as bulk ferric sulfate is applied 100 milligrams. If this is 100 milligram per liter, so how much alkalinity to be supplied? I will write this equation. Call is dropped. This is the equation. So the iron is present 100 milligram per liter and whatever is given I am writing 100 milligram per liter as bulk ferric sulfate, bulk ferric sulfate, and uh, so and it is 20% by weight. Ferric sulfate is iron is Fe is 20% by weight in bulk ferric sulfate. So from the above equation, from this equation, we can say like three equivalents of Fe3 plus is reacting with three equivalents of SO3 minus, or we can say one equivalent of Fe3 plus is reacting with one equivalent of SCO3. Correct? So how much equivalent of Fe3 plus is present? So I can write it as 20%. I will write it like 100 milligram per liter is Fe. Out of that, 20% is the iron and This is given weight, so it is in milligrams, so I will convert it into grams, 10 to the power minus 3, 3 grams, and given weight by how much is the equivalent weight? Molecular weight. So molecular weight of iron is, yeah, we write it again, it will be better. So, in the previous lectures, we have studied equivalence. Equivalent is given weight by equivalent weight. So, give, and what is mole? Mole is given weight by molecular weight. Given weight by molecular weight. So, we know the molecular weight. So, what is equivalent weight? Equivalent weight is molecular weight by combining capacity. This we studied in the previous lectures. So for this Fe3 plus, it will be molecular weight divided by 3. The combining capacity is 3. And the molecular weight of iron is how much? 55.8 by 3. So equivalence of Fe3 plus will be given weight. How much given weight? It was 100 milligram per liter. So let me write it as 100 into 20 into 10 to the power minus 3. It will be in grams, and that will be 20%. So 100 into 10 to the power minus 3 grams into zero point 0.2 given weight by equivalent weight. It's 55.8 divided by 3. We will solve it. How much we will get? So it will be 10 to the power minus 3 equivalents. As we know, one equivalent will react with we'll write it like this. What does equivalent concept say? N1 V1 is equals to N2 V2. So it says one equivalent of anything reacts with one equivalent of any other thing. So one equivalent of anything, one equivalent of this thing reacts with one equivalent of any other thing. So this much amount of Fe will require this much equivalents of alkalinity. So amount of alkalinity required is how much? This much only. 1.07 minus 3. So if you multiply it with so one equivalent of alkalinity as CaCO3 will be 50 milligram per liter. We will see how is it 50 milligram per liter. So we know CaCO3. So what is the molecular weight of CaCO3? Ca is 40, carbon is 12, oxygen is 16 into 3. So it will be 40 plus 12 plus 48. So it will be 100 grams. So in 1 mole there are 100 grams. But what is so this is the molecular weight. So what is the equivalent weight? So the equivalent weight is molecular weight by its combining capacity. So 100 divided by its combining capacity. So for CaCO3 it is Ca2 plus Ca3 2 minus. So its combining capacity is 2. So its equivalent weight is 50 grams. So it means in one equivalent there are 15 grams of CaCO3. So one equivalent of alkalinity as CaCO3 is 50, it's not 50 milligram, it will be 50 grams. Let me correct this. It will not be one equivalent. We can write it as one equivalent per liter of alkalinity as CaCO3 is 50 grams per liter. Now it is correct. So amount of alkalinity required will be 1.07 and 10 to the power minus 3 equivalents. Now we will multiply and we will get the final answer. Total alkalinity required will be number of equivalents of iron, which we calculated 1.07 and 10 to the power minus 3 equivalents into 15 into 10 to the power. Total alkalinity required, this will be equivalents per liter into 10 to the power minus 3 gram per equivalents as CaCO3. How much it will be? This will be cancelled. 1.07 into 50. So it will be milligram with soil. Because we have multiplied it with 10 to the power 3. Into 50 milligram per liter as CaCO3. So it will be how much? 1.07 into 50. So it will be 53.763. 53.763 milligram per liter alkalinity as CaCO3 required. Now there is one more question. Determine the daily requirement of alum, lime and polyelectrolyte to coagulate a flow of 100 liters per second if the jar test indicated that optimum coagulation occurs when 1 liter of water is dosed with 3 ml of 15 gram per liter alum solution, 1.8 ml of 5 gram per liter suspension of lime, and 0.2 milligram per liter of polyelectrolyte. So this is the last question, which says determine the daily requirement of alum, lime, and polyelectrolyte to coagulate a flow of 100 liters. So we will write one by one what is the data given to us. You can follow it. So the flow is 100 liters per second. The flow is 100 liters per second, and so first we will calculate what we need to find. Daily requirement of daily requirement of alum, lime. Number C is polyelectrolyte. And what is given? What is given to us? The flow is 100 liter per second and optimum coagulation dose for, and we are given optimum dose of alum. When 3 ml of alum is added, but 1 liter of dosed with 3 ml. So the optimum dose is when this 1 liter of water is dosed with 3 ml of alum. And what this 3 ml consists of? So this 3 ml is taken from 15 gram per liter. So what we will do? This is 1 liter beaker or volumetric flask we will take. We will add 15 gram of alum in that. Okay. And then from that 15 ml we will take 3 ml. So in reality how we will do, we will see. You can understand. So what is being done here? We are taking 15 gram of alum. 15 gram we are taking means 15,000 milligram in 1 liter. Means 1 liter means 1000 ml. So it will be 15 milligram per ml. And then we are adding how much ml? 3 ml. 3 ml means 3 ml into 15 milligram per ml. That will be 45. Then it will be 45 milligram. 3 ml. Then we are adding 45 milligram in 1 liter. To get the optimum dose of alum. So likewise we are doing this for every time. So likewise 3 ml of 15 gram per liter of alum solution, 1.8 milliliter, 1.8 milliliter of 5 gram suspension of lime and 0.2 milligram of polyelectrolyte. So this we are taking. Let's calculate one by one. So daily dose of lime required. Let's see. Daily dose of lime required. So first Daily flow, let's calculate. Daily flow. Daily flow is how much? 100 liter per second. I think, let me check. Yeah. So per minute, per hour in a day. So that will be 100 into how much? 86400 liter per day. I think it will be 86.4 into 10 to the power 6 liter per day. So amount of alum required. Amount of alum required per day, or we can write daily also. So it will be 86.4 into 10 to the power 6. That is liter per day. So how much we are adding? We are adding 3 ml into 15 milligram per ml, or then let's write it in original form. 15 gram per liter. Let's convert this into 10 to the power in liters. 86.4 into 10 to the power 6, 3 into 10 to the power minus 3 liters, and convert this into kg. So this will be cut. Things left will be 86.4 into 3 into 15. Let's calculate this. Here's a mistake in calculation. So it will be 8.64. 8.64. Here also we need to change. 8.64. 8.64. Here it will come as 388.8 kg. kg per day. This is the amount of alum required per day. Now we'll calculate. Daily dose of lime requirement.